So today we're looking at quotients of polynomial function. This will lead into graphing. Now you already know what asymptotes are, but there are some formal definitions of vertical asymptotes, and we talked about that on Thursday. How if you look at a like even a relationship like y equals x minus 3, just a straight line, and then you take the reciprocal of it, 1 over x minus 3. The relationship between those two functions, right? So where the first one crosses the x-axis, it's equal to 0. There's an asymptote there. There's a vertical asymptote there. And so vertical asymptotes don't only occur in this situation. There are other kinds of, lots of other kinds of functions. But for us right now, looking at rational expressions, they occur when the denominator has a 0. Like when the denominator would be equal to 0, that will give us a vertical asymptote. And we talked about that, like I said, on Thursday. So horizontal asymptote, we saw those, but we didn't like talk as much about where they come from. So they are straight horizontal lines, obviously. They are of the form y equals b. And it's not quite as clear, but we'll see exactly where they come from in a moment. Where b corresponds to a y value, where similar to a vertical asymptote, where the function itself has no value. Some value where there's no solution. And it's not as clear to see when that would happen. It's not when the numerator is 0. If the numerator is 0, that's fine. The whole function is just 0, right? But we'll see in a few moments where that comes from. And then there's this other thing called, and horizontal asymptotes only occur if the degree of the numerator of a rational function is less than or equal to the degree of the denominator. So, that maybe if you can memorize that will help you sort of look at it. But you'll probably be fine with horizontal asymptotes. Oblique asymptotes are straight line, but they're not horizontal or vertical. And they are still asymptotes, so lines that the function approaches infinitesimally closely. That means like closer and closer and closer, so small that it's kind of going, the magnitude is going to infinitely small, but never touches. And they're of the form y equals mx plus b, like they're the equation of a line, because they're just some straight slanted line. So they're called oblique asymptotes, or we call them slant asymptotes. And these ones occur, this is important to know, when the degree of the numerator is exactly 1 more than the degree of the denominator. Okay, so then we know that there is a slant asymptote or an oblique asymptote, but we're not going to worry about finding them, at least not yet. Okay, and then the last thing that you probably haven't seen before is a hole in a function. Yes? Do you know what degree, like the degree, so like if it's a quadratic or a cubic or something like that, right? So the degree of the expression in the numerator. Because up till now, you're right, we only had like a 1 up there. But you could have x plus 3 over x squared minus 4 or something like that, right? That's kind of what we're looking at now, more like rational expressions. And so you look at the degree of those. And a hole in a function is a bit strange, but usually like the function just looks like a normal function and it has one little spot that it just doesn't exist. So everywhere else it's fine. Not always, sometimes there's asymptotes and such as well, but often you'll find that they're good everywhere else and there's just one value that they don't work for. And that occurs when there is a common factor between the numerator and the denominator. And that common fact, well, we'll see it in a moment. We'll talk about it in a moment. Okay, so that's just some definitions. So what we're going to do is we are going to look for holes and vertical asymptotes in each of the following. So first, we want to factor everything. There's not a ton of that today. Not like the rational expression stuff, but once in a while there's a little bit. So let's factor this one. right? So nothing going on in the numerator. It's just a constant. So the denominator, we've seen these kinds have vertical asymptotes of x equals -3 and x equals -4. And that's it. Easy one to start off. When we talked about this on Thursday, we were comparing it to the reciprocal function. And so we were looking at asymptotes as equal to 0 when the reciprocal graph was equal to 0. But we can also calculate that the denominator is equal to 0. Those things, that's something that's very familiar because we do that when we solve quadratics and all sorts of things. So let's take a look at what this graph would look like. X squared plus 7x plus 12. So there you go. There's your two vertical asymptotes at -3 and -4. Okay, next one. Does anybody notice anything about this one? Bottom's already factored. There's a common factor on top. Watch out for those. So this is what it looks like when there's a hole in the function. Okay. What would happen? So we have a vertical asymptote at when x equals -2, and it looks like we have a vertical asymptote when x equals 1 as well. But it doesn't work that way. Because it's a common factor with the top, it's actually a hole. Let's see what that one looks like. So 3x minus 3 is our numerator. And our denominator is x minus 1, x plus 2. So there you go. See that hole? So the graph is normal. It would look like a normal reciprocal function of 3, our common factor, over x plus 2. Like that's what the rest of the graph would look like. 3 over x plus 2. Except it has this hole where x equals 1, because it's not just an asymptote, but it's 0 on the top and the bottom. So it's 0 divided by 0. It doesn't make any sense, obviously. And when those factor out, it allows there not to be an asymptote, but it can't exist at that space. So we have a hole when x equals +1. Nothing hard there, but sometimes we miss it. Like sometimes it's tricky because you miss the common factor. Good so far? Okay, so let's take a look. So that's vertical asymptotes and holes. Pretty straightforward, I think. Horizontal asymptotes, how do we find those? For what value of y does this function not exist? So what I'm going to do is I'm going to just pick some value. I don't know what it is. Let's say it's a, where this function doesn't exist. Okay? And so a equals 2x plus 3 over x plus 2. And if I want to solve for x to find out what x value it is where this doesn't work, what would I do? Well, I would take the denominator, I'd multiply it. So a times x plus 2 equals 2x plus 3. And so this would give me ax plus 2a equals 2x plus 3. Now, it's not obvious, but if the coefficient of the x on the left was the same as the coefficient of the x on the right, what would happen? So if I had 2x on the left and 2x on the right and I tried to solve, they would subtract, right? They would cancel each other out. And you'd end up with 2a, whatever a is, equals 3. Something that's not 3 equals 3, which makes no sense, not possible. Do you see where I'm going with this? So when we look at it like this, let's just let a equal 2. We're just messing around here. Like this is not something that you will do. We're just messing around and experimenting here. So I've got 2x plus 4 equals 2x plus 3. So 4 equals 3. It's not possible. So it turns out we have a horizontal asymptote at y equals 2. How did we figure that out? Well, we messed around and we found this value for y. I put a in for y. So y equals 2. When y equals 2, I would have a horizontal asymptote at that point. So let's see what that one looks like. 2x plus 3 and x plus 2. Horizontal asymptote at y equals 2. That's what we mean by that, right? It's a line. It's a horizontal line. Equation of a horizontal line is y equals 2. Vertical asymptote at -2. That's an easy one, just when the denominator equals 0. Okay, let's take a look at a little bit of a trickier one. So we're going to do the same thing. We're just going to stick in this a. And I get 2ax plus 5a equals 3x plus 1. What do I have to put in for a so that this doesn't work? How do I turn 2ax into a 3x? Yes. Say that again. 1.5. What's another way of writing 1.5? 3 over 2. If I put 3 over 2 in, so 2 times 3 over 2x, the 2's divide to 1 and I get 3x plus 5 times 3 over 2. It doesn't really matter, 15 over 2, what that is, equals 3x plus 1. And the 3x's are going to add to 0. They're gone, and I get something nonsensical. So what's the pattern here? What will always work? Does anybody, like, where did the 3 over 2 come from? Coefficients of the x. Will that always work? So 3, like this 3 over this 2. Like if you just kind of visualize the algebra, when you move the bottom over, that's what will always cancel it out. So there's actually a really easy way to find horizontal asymptotes. So in this case, it's y equals 3 over 2. And that's actually exactly what you do. You just take the coefficient of the x's, the numerator coefficient over the denominator coefficient. Does that make sense? So there's a 3x on top, a 2x on bottom. So my horizontal asymptote is 3 over 2. Yes?
If you had 2x squared terms instead, would you just take the coefficients on the previous?
Although we won't probably really see that at all. Okay, so now we can do a little bit more, determine the vertical and horizontal asymptotes, any holes, and only if there is an oblique asymptote. So we're just going to notice if there is one. We're not going to find the equation of it. We're going to see what it looks like in a function. Okay, so this first one, where are my vertical asymptotes? You can find those. Somebody want to give me the first one or one of them? Vertical asymptote. Yep. Good. So x equals -1/2 and 3. Now this if you look back at the definition, it says horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. So the degree of the denominator is 2. That's a quadratic on the bottom. The degree of the numerator is 1. So it does have horizontal asymptote, but it's a little bit different. This is not the kind of function that we're going to do a lot with. But you can see that there is one, but it's, well, I guess you can tell if we zoom right in, you can kind of see that there's one, but it's not exactly what you might expect. So when the degrees are different, finding it is a little bit different. We're not going to worry about that too much right now. Okay, so the next one. What do you think? Do you notice anything about this?
The degree of the numerator is 1 more than the degree.
Is exactly 1 more. And so take a look at what it looks like. So there's a slant asymptote. That's what it looks like. There's an asymptote running, and it's not showing it. Yeah, it's not showing it. Running along here. Okay. So, and you might think that it would have horizontal asymptotes, and not to say that it's impossible, but in this case it certainly doesn't. But it does have, so this one has an oblique asymptote and has a vertical asymptote at x equals 0. So it still has the same vertical asymptotes, but that one has an oblique asymptote. Next one, so vertical asymptote is easy. X equals -1/3. And what else does this one have? Good. Y equals 2/3. 2/3. Okay, and the last one looks like it has a vertical asymptote at x equals -2 and a horizontal asymptote at 2/3. Like that's kind of what it looks like. But if I factor it, I get a common factor on top and on bottom. They both have a common factor, and I get a common factor on top and on bottom. So what does this graph look like? 2x plus 4 over 3x plus 6 is actually a straight horizontal line because the common factors on top and on bottom divide to 1. And so essentially, this is y equals 2 over 3. It's just that horizontal line. But it has a hole at where x equals -2, where that common factor would be 0, is where it doesn't exist. And that's what I mean by they often look like just a normal kind of function, but there's one spot where they don't exist. So this one has a hole where x equals -2. Okay, so I'm just going to go back and put a couple more of those back up. So here's a, x plus 1, whoops, x plus 1. So think about the graph and 2x plus 1, x minus 3. Kind of looks like those ones that we were graphing before, 2 vertical asymptotes where the denominator is 0. So like these are clues that you're looking for. Part of your work is going to be matching graphs to their equations. So think about looking for those clues in the graphs. What was the next one? X plus 3 all squared over x. So this is the one that has that oblique asymptote. And a vertical asymptote. And then that regular one, 2x minus 3. Let's do that. And 3x plus 1. So horizontal or vertical asymptote at -1/3, horizontal asymptote at y equals 2 over 3. Any questions? Pretty straightforward, I think.